topic du jour. Okay, we're gonna play a little calculus Jeopardy for a second. All right, here's the way, and this isn't just for fun. I mean, although this does come at sort of an opportune time right after spring break, but there's a reason for this. We're going to give this process of playing calculus Jeopardy a name here shortly, and it really is something important that we're going to do. You guys all know how to play real Jeopardy, right?
No.
Yeah. Okay. Okay. So you're given the answer, and then you're supposed to provide. Yeah, the question exactly. So you the way they say you give the answer in the form of a question. Okay. So the answer.
Oh, you're right.
All right, here we go. Here we go. I know you got lots to catch up on. We'll maybe get to that at the end here.
What is 6x?
What is 6x? No.
No.
Right here. Oh,
What is x cubed? What is x cubed?
What is x cubed? Exactly. Okay.
The answer, the derivative is easy. Oh, I get it. Right. This is the derivative. It's pretty hard. Nobody thinks like that. Nobody thinks of questions.
Okay, we good? Get the idea? Is that the only answer you could have given me?
What is no? Yes.
Say it again.
What is how?
Okay, now you're close, close. We could have also said, hold that thought. We could have also said, what is the function x cubed plus any constant? Yeah, we could have said x cubed plus 7 or x cubed plus pi. To capture all those possibilities, we could say something like this: x cubed plus c, where c just stands for some as yet undetermined constant. In fact, we could say it's an indeterminate constant. Okay. Now, what we just did there, that's called an antiderivative. Not surprisingly, because it's sort of the antagonist of the differentiation process. Is the anti-differentiation process. It goes the other direction. So the antiderivative of 3x squared is x cubed plus c. Because if I take the derivative of this, I always get that back, right? Okay, make sense? Okay. So let's give this a name. So then we'd call this an antiderivative, or the synonym for that is an indefinite integral. We're going to call it an antiderivative for now. Indefinite integral will make more sense a little bit later. It relates to something called a definite integral. And really, when we start doing definite integration, then indefinite integrals, it makes more sense why we call it indefinite. Although really, you kind of probably could make a guess right now. It has to do with that, right? Because we don't know what the constant is, okay? But just fine to call it an antiderivative. Okay, so then, if we want to be a little bit fancier about this, and of course we do, we can use this to solve a new class of equations called differential equations. Monday and Tuesday. After a long break, you gotta give me a little slack here. Oops. Jeez.
Wow.
Okay, differential equations. Sounds really impressive, and hopefully, all of you will go on and continue with your math studies, and if you do, you're guaranteed to do lots of battle with differential equations in college. Kind of the way the college curriculum will evolve for you if you go, if you go straight math, and I'm not talking statistical science here, but if you just move forward in math, you're going to take some more calculus. You're going to do probably 2 more years of calculus. Well, I don't know if you do 2 more years. You'll do at least 2 more classes of calculus, maybe 3, where you'll deal with lots of 3-dimensional stuff, and you'll sort of learn to apply the things we learn in here to sequences and series and things like that. Although none of that is any harder than what we're doing now, I promise you. It's just sort of an extension. In fact, it's probably harder to learn it the first time, but once you get it, extending it to those venues is really not that big a deal. After that, what you'll do is you'll take some classes, and this is more specifically if you're going into, say, engineering or physics or math or something like that. Take a series of classes that deal with just solving differential equations. Because as we're going to see, even now we kind of get a sense of this. Differential equations are the backbone of everything. It's the physics. Differential equations allow us to take situations that aren't just static. Now, static situations, you don't really need them for. If you're building a bridge, for example, you don't need to do a lot of work, some, but not a lot of work with differential equations, because nothing's moving. Excuse me. But when things start moving, if you start to want to capture, say it again? A drawbridge. There you go, a drawbridge. Or if you want to look at the behavior of, say, a plucked string on an instrument, you want to study what the vibrational nodes and antinodes are going to be. There are going to be harmonics on the string, and it's going to wave in certain ways, and there will be superpositions of all these different waves on a string that give it these complex sounds. Music, you'll find, is very mathematical. Then you have to start to look at things called differential equations, because they deal with a changing situation. That's what calculus captures that non-calculus really is incapable of dealing with. Now, if we want to give it a definition, and I guess to finish my little story about your futures, you're going to probably take 2 to 3 of those. Remember, I took a differential equations class and then 2 partial differential equations classes, and that was enough. I mean, then you're pretty well versed, and you can start to specialize in some area. But you'll see these guys again. Now, what are they? Differential equations have gotten easier to deal with. Back in the old days, I'm trading my age here. We didn't have all these fancy graphing utilities and computer algebra systems to deal with differential equations, and there was almost a little bit of art involved. And that's good to know, some of that, and that's for later. But there are also, as you're going to see a little bit, even here this year, there are some ways using, for example, it's hard to do. The TI-84s really don't do it, but TI-89s do. And there's some, and if you, anybody have a TI-89? Got one? I've got one too. You guys can play around with it a little bit. There are some other computer-based software that help us to kind of deal with these things also in a way that's not so algebraic, which is a little more numerical, a little more graphical. And we'll get to that later on in the year. What is a differential equation? Differential equation is simply, and this is it, an equation. It's going to be very anticlimactic. With one or more derivatives. That's it. That's a differential equation. Okay. Now, why is that such a big deal? Well, because if we want to deal with situations that are changing, we'd have to have a derivative, wouldn't we? Because a derivative means, like if I say something like dv dt, what does that really mean?
Acceleration.
Say it again. True. Yeah. Okay. Specifically, you're right. It is. But maybe that's not velocity. Maybe that's volume or something. So pretend it's volume. And I don't really want to know what physically that quantity means, but how would I describe that? Yeah. Okay, the derivative of volume with respect to time. Another way of saying that would be the rate of change of volume with respect to time, right? And notice the key word there is change, right? Things are changing. If we were to look at, for example, if this is volume versus time, we've done some of this stuff. We always want to try to think two-dimensionally here, graphically, that is. If I'm graphing volume versus time, and I'm looking at, say, a balloon or something, the curve is going to go like that, isn't it? Right? The greater, if this is how it's changing, well, maybe. I mean, depending on what the function is, but it could change like that. It can change however we want to. But what we know here is that it's not necessarily linear. For certain times, the rate at which volume is increasing is different than at others. Maybe even a better way to think about that would have been dV dr or something. If I did dV dr, and this is the radius of the balloon, then it really would look like this. Okay. As the radius increases, volume is captured at a larger and larger rate. Right? And we've all seen that when you blow up a balloon. I think I mentioned this earlier. Initially, it seems like it's pretty easy to do. You blow it up in a few breaths, it starts to get kind of big, and then after a while, you keep puffing and puffing. It doesn't get a lot bigger because the radius is increased, and it takes a lot more volume to push that radius out there. There's this differential rate of change. So you can kind of get an idea here that when you want to deal with things that are changing with time or variables that are connected in some nonlinear way especially, this is the only show in town. So we got to learn to deal with these. And it's really fun stuff, and it's kind of gives you some real insight into the way the world works, but we got to start at the beginning. So let's take an example of a simple differential equation. There's one. Very simple, right? Kind of use some shorthand notation there, but what does that say? Say it again. Yeah, the derivative of y with respect to x, or y prime for short, equals 2. Now, what do you suppose the solution of a differential equation would involve then? Okay, we got to undo that derivative, right? We want to come up with the equation that we could differentiate to create that differential equation, right? We want to come up with the function that could be differentiated to give us this result, right? Are you starting to see why that calculus jeopardy is going to come in handy? That antiderivative, because that's how we reverse the differentiation process and sort of quote-unquote undo a derivative, is by executing the antiderivative of both sides, right? So we could just do this without, we won't be formal at all about this. Let's just play a little calculus jeopardy. Well, this is the answer. What's the question? If the derivative of the function is 2, then the function is
2x plus constant.
Yeah. Everybody agree?
Yes.
How could we check?
Take the derivative.
Take the derivative, right? Okay, and we haven't used any rules yet, right? Notice that this is just all, you're just kind of finessing your way through this because you're smart. We're going to come up with, we can actually turn this thing around, and all the stuff that we've learned, here's one of the fringe benefits. We get a ton of, we get essentially double what we get from the class here in the course of about a day. Because all the rules that we've learned for differentiation, obviously you're going to convert into reverse directions, and we'll end up with the antiderivative rules that accompany them, right? So even stuff like, I mean, this is really just the power rule, isn't it? Well, okay, yes. The antiderivative chain rule, yeah, it gets a little tricky. And I'm not going to lie to you, antiderivatives are harder than derivatives. They really are. Derivatives, here's kind of a saying that, if I'd said this earlier, you probably would have thrown stuff at me, but you're probably starting to kind of get this sense. Derivatives, in the grand scheme of calculus, derivatives really aren't that bad because all you have to do is follow directions. You have to just follow the rules. Now, the rules are a complicated set, and sometimes following those rules can be a challenge. But once you get the hang of how to follow the rules, aka the chain rule, and then all the other assorted rules that would fall under that. You got the trig, the trig derivatives and the power form, the power rule and all that stuff. Once you get a handle on all that, really, derivatives are not a big deal. You just follow those rules. Now, antiderivatives, it turns out, are a little trickier, and you'll see why. But that just makes them more fun because they're more challenging. So then what we would say is this right here is the general solution of that differential equation. Okay. It's general because we haven't pinned it down. I want to show you something here that's kind of, and this is really important. It may not seem like a big deal, but let's just take this exact function. Let's take the function 2x. We did something exactly like this. I don't remember what the function was, but we did something exactly like this earlier in the year, and you'll remember this. Where if I take the function, let's say, y equals 2x, so that's just going to look like this. Right? So there's y. If I want to sketch a graph of y prime, that wasn't too big a deal, was it? What did the graph of y prime look like if I'm given the graph of y? It's going to be a horizontal line, isn't it? With a value of what? Say it again? 2. Yeah. Right? It's going to be 2 because the derivative of this is 2. The slope of this line is 2 everywhere, and the value of the derivative, right, equals the slope of the function, right? And we can get that either visually by just, by noticing graphically that the slope is 2, or by differentiating. Right? We get y prime equals 2. And so here's my y prime function. Okay, and then finally, what's y double prime in this case? Yeah, good, because the slope of that line is 0. And we're doing a bunch of this. So y double prime equals 0. Now, if we start with a given function, these derivatives are exact, aren't they? There's only one answer for y prime. It's 2. Agreed? Okay. Only one answer for y double prime. It's 0. Now, what happens if we reverse that process? Let's pretend that we started down here instead and work the other direction. Okay. If we started with the second derivative, or with the first derivative, let's start there, being 2. So here's the graph we're starting with. What's the first derivative, or what's the function going to be that goes with that? 2x plus c. I could have a whole bunch of them. And in fact, what we're going to call this is a family of curves, because c could have any of an infinite number of values. C is just some constant. Let's just graph a couple of those. Here's the one. Here's y equals 2x plus 0. What if I do this guy right here? Well, that's just y equals 2x minus 2, right? And I could, there's a whole bunch of those. I could graph right here, an infinite number total, and I could get a whole bunch of those on here that kind of show you the nature of that family of curves. If you had to describe that family of curves, what would it be? All of the functions with slope 2, right? All lines with slope 2 are in that family. How do they all end up if we, once again, reverse directions and work back down the ladder? If I take any one of these, what we call trajectories of the family, any single curve from within a family of curves, we call a trajectory. I'll write that down. Trajectory of the family. If I differentiate any of those, because their slopes are all 2, I'm still going to get that answer, right? Make sense? Okay. So, oops, no, it is right. Okay, so then, So then this is a general solution because it includes all members of the family or all trajectories. Now what if I want to specify a single trajectory from that infinite family? Going once again back to my picture, I guess. What would I maybe have to do? Any ideas? No, nothing like that. How can I pinpoint an infinite number of lines that I could nest together there with all having slope 2? How could I pinpoint exactly one of those? Let's just be really philosophical about this for a second and tell me what is a function? What do those lines really mean? They're kind of, yeah, I mean, we put stuff in, and I see what you're saying. Yeah, it's like a machine. We put in input values. The function machine spits out output values. Anytime I want to graph a function or a curve, whatever we want to call it, it's just an organized locus of points. Locus is just a fancy math word for set. It's just a set of points that have a specific relationship, right? And the easiest way for us to illustrate or articulate that relationship is with an equation, right? If we have the equation y equals 2x, that tells us exactly what the relationship is between any x value and any y value, right? Now, if we turn that idea into look at it through a graphical lens, all of these trajectories, in this case the lines, are merely collections of an infinite number of points that are strung together like beads on a necklace, right? Strung together in the shape of a line, right? But wouldn't you agree that if I'm talking about an individual trajectory or one of those lines in that family, all of the points, in this case, all of the points on that line are unique to that line, right? There are an infinite number of other lines in the family, but they're all going to be different sets of points. So now, given that, how could I specify one of those lines? What would I have to do to specify one of those lines as opposed to all the other infinite brethren in that family? Choose, what do you mean? Okay, true. Choose a constant. That's true. That's true. I could choose a constant. And ultimately that's what we're going to do. But based on that idea that a line is just a set of points, choose a point. It wouldn't even have to be the starting point. I could just choose a point, right? Couldn't I say something like, I want to find solve the differential equation y prime equals 2, but out of that infinite number of lines that I get back from the family of curves, the general solution, let's specify the one that goes through the point whatever. Let's say it goes through the point x equals 1, y equals 2, how about? Okay, so where is that going to be? Well, x equals 1, y equals 2 is right there, right? So if I'm going to specify that point right there, then that means this is the line that we're specifying, right? Okay. And now that gives us back, if I add this additional caveat here, now we don't have an infinite family. We have picked just one curve out of that infinite family. In fact, we've been very particular, and we've come up with what's called a particular solution. Okay? How do we do that? So we've seen it graphically, but what if I want to take this differential equation, y prime equals 2, and we're going to choose the particular condition. Now, a lot of times books, and I can't remember, I think that the Math Excel book makes this, does this. It's not really a mistake, but it's just something that I don't totally agree with. They call it an initial condition. That's because I'm coming from a physics background. A a particular condition doesn't necessarily need to be initial, because what does an initial condition really imply? What's the word initial mean? Starting point. So typically that's going to be, let's just say we're looking, as we do in physics almost exclusively, let's say that we're looking at a function of time. What value of t is that implying? 0, right, when we start the stopwatch. And so an initial condition usually implies that the independent variable is going to have a value of 0, but that doesn't have to be the case, right? So that's why it really is, just so you're aware of this, at least this is my bias, I think it's better to say particular condition and reserve that word initial for when you're specifically plugging in 0 for the independent variable. But I don't think this book does that, and it's really not a big deal. Either or. So if I want to do this, then I want to come up with the exact trajectory that's going to solve this differential equation and is going to satisfy this condition. So when I plug in x, y equals 2, that just adds an extra step to our process, doesn't it? You guys already did the hard work, wasn't so hard. But you told me that when we play Calculus Jeopardy, we just get back y equals 2x plus c. Okay? Now Josh wisely suggested that if I want to get a specific trajectory, that really just amounts to choosing a constant. Well, it does. It does. That's what we're going to do here. What do you suppose I have to do to turn this general solution into a particular solution if I know that I need to go through the point 1, 2? Yeah, I'm just going to plug in the numbers for x and y, aren't I? Right? I'm just going to plug in 1 for x and 2 for y and get 2 equals 2 times 1 plus c. And if I solve for c, what do I get? Okay, makes sense? So we went from the general solution down to the particular solution. Okay. And that's anti-differentiation. That's really the main topic for the rest of the year is doing antiderivatives and integrals. That's a big topic. Okay, so last thing I want to plug in today. Last thing. Okay. I've been trying to resist the temptation to throw a whole bunch of theorems at you, because I think that just sort of, to me, it's almost better to go back and look at those once you get the concept and you practice the skill a little bit. Then the theorems aren't that big a deal. I'm gonna just probably have to throw 1 or 2 at you right now, though. At least some ideas like that. So, okay, so if I'm going to call this the derivative function. In this case, dy dx is it's going to be some function f of x. I didn't call it f prime. It's just some function, right? Keep in mind that when we're anti-differentiating, we're starting with the derivative function, in this case 2, and we're working backwards to come up with the antiderivative function. That make sense? So it really does make sense for us to think of the derivative as being some starting function that we're going to undo. Now, something that I didn't spend a lot of time on in chapter 3 that now is when it makes sense is this notion of a differential form of a derivative. You guys did a bunch of stuff doing approximations with differentials, but it turns out that you can write any derivative in differential form just by multiplying both sides algebraically by whatever the denominator of the derivative is, right? So if I want to put this into differential form, it's just going to look like this. dy equals f of x dx, right? Okay, now if my goal is to find out what y is, isn't y just going to be equal to the antiderivative of dy, right? You're trying to undo the derivative, right? Here's our calculus notation for that. It's a lowercase Greek s for sum. And it's kind of a weird looking thing. You might have seen this on your calculators or seen it on, you've probably seen it before somewhere. But it's just this kind of, and that's not supposed to be there. It's just this. Just kind of looks like that. Okay, and whatever you're taking the antiderivative of goes inside. Okay, so really what we're going to do is we're going to just put this stuff inside the antiderivative, the integral sign. And so to solve this guy, we're going to have the antiderivative of f of x dx. Okay. That's our new notation. That means antiderivative. And the result of this is going to be whatever Calculus Jeopardy tells us, right? So if we looked at that last example we did, it would have looked like this. We would have had the antiderivative of 2 dx equals, what'd you tell me for the answer? 2x plus c. Because the derivative of this is that. Okay, so that's how we write these things. If we want to solve a differential equation, this is the new, admittedly weird notation that we use, is this integral notation. Okay? If we want to really get specific about the anatomy of an antiderivative, I'll show you an anatomical diagram. Okay, so we'd say that this is the integral sign. Okay. This is the variable of integration, right? X. That sounds mysterious, just the independent variable. That's all it is. This part in here is called the integrand, and that's just the question that's being posed in Jeopardy style. And then this part right here is the, well, this whole thing I should say. Is the antiderivative. Notice there's a capital F and that's an F. They're different, right? They're related, but they're different functions. All right. See if we can string this together into one problem. The whole thing. Solve a differential equation. So how about, let's take one out of the book. How about? Is it hot in here? Just me. It's hot too. A little hot. Okay, let's try this one. Let's solve. Let's try that one. Let's solve this differential equation, y prime dy dx equals negative 1 over x squared. And let's find the general solution, then let's find the particular solution that passes through the point 1, 3. Okay? So how do we, first things first, how do we set this thing up as an integral? So we can look like calculus students. Okay, good. So we're going to write the derivative in differential form. So we're going to write this as dy equals this whole thing, negative 1 over x squared dx, right? Agreed? Okay, so y is going to equal then, right? Y is going to equal the antiderivative of this thing. And if we want to write that using our fancy new notation, it's just going to look like this. Right? And now we get to play calculus Jeopardy. Now we're going to come up with some rules for this, within the next couple days. But for now, let's just see if we can almost by trial and error come up with the antiderivative of this. The derivative of what is going to equal, and if maybe it's better to write that as like just a negative power. How about? Yeah. Instead of 1 over x squared, how could we write that? Okay. So what do you think? So I'm hearing some good, so should we just try some? At this point, we're just going to kind of go trial and error. Somebody throw one out. X to the negative 1? Okay, let's try that. So the proposal is that this is equal to x to the minus 1 plus c. Okay, if I differentiate that, does it work? If I take the derivative of this, I'm going to take the number out front, right? This exponent out front and get negative x to the negative 2 plus 0. So it worked, right? So that's our answer, isn't it? Because that's the derivative, that's the function that we would have to differentiate to get this integrand, right? So there's our general solution. Oops. Okay, let's find the particular solution. What do I have to do to find the particular solution? Plug in this 1, 3. Okay, plug in 1 for x, 3 for y, and I've got the equation now. Remember, we've got the equation y equals 1 over x plus c. So if I plug in 1 for x, I get 1 over 1 is 1, right? So what's c? 2. If c is 2, then all I have to do is plug 2 back into c in the general equation, and I get the particular solution. Y equals x to the negative 1 plus 2. Okay? All right. Wow, that was more than I hoped for in one day. That's pretty good. We'll come back and take another look at that. But I just wanted, that was my goal, is to get you to a point where you could see how to construct a differential equation. There's a lot more theory that goes into this, but that's 95% of it.